Okay, guys, we're going to look through the second of the March 31st homework questions. This one's about moments and turning forces. I've actually written a little bit on the question because I've had to re-record this. There was a load of beeping in the background. You couldn't hear what I was saying. So let's get cracking. Okay, what do we got? Define the moment of a force. The moment of a force is force times the perpendicular distance to the fulcrum. A toy such as that shown has a heavy hemispherical base and its centre of gravity is located at C. When the toy is knocked over, it always returns to the upright position. Explain why this happens. Now, trying to do this verbally is tricky. A diagram will help, but the thing is you can't just do a diagram for this. You're going to have to need to explain what happens. So let's see if we can picture what happens first. Imagine that this terrifying clown thing, actually no, it's quite a happy looking clown to be fair, isn't it? Like a horror film clown. I'm still not going to draw him properly though. You've got your weight there acting here. Let's imagine that he's been knocked over. The point of contact with the ground is here, and the weight is applied over this side. So there's going to be a horizontal distance which will cause a turning force, causing it to rotate in that direction, as in back towards the vertical. If it was to go past the vertical, again you'd have the turning point there, contact with the ground, weight acting downward on this side, causing the turning force to rotate him back into the vertical position until his centre of gravity is centred. Okay, so kind of verbally, the trick with that is to say that whenever it's displaced, there'll be a turning force around the fulcrum at the bottom of the toy, causing it to rotate back into an upright position. Okay, that's part A. Part B, state the conditions necessary for the equilibrium of a body under a set of coplanar forces. So this is that experiment we did with the meter stick suspended from the Newton meters with the weights hanging down. And to be in equilibrium, two conditions had to be met. One was that the sum of all forces, so the sum of all vector forces, was equal to 0. Or you could say that as the forces up had to be equal to the forces down. That's the first condition. And the second one was that the turning forces also had to equal 0. Had to sum to 0. So that if I took the moment from any point along this object, the total turning force in the counterclockwise and the counterclockwise directions should be equal. That's in order to have equilibrium. Okay, three children position themselves on a uniform seesaw so that it is horizontal and in equilibrium. The fulcrum of the seesaw is at its centre of gravity. A child of mass 30 kilos sits, blah, blah. Okay, sketch this out, all right? Definitely way easier to get your head around when you sketch this out. So we've got a seesaw. The fulcrum is at the centre of gravity, so we don't need to consider the weight of the seesaw itself, which is handy because it acts at the fulcrum. So there'll be no turning force resulting from that. And we've got a child at a distance of 1.8 metres to the left. And that child is 30 kgs in mass. Distance is 1.8. I've got another child at 0.8 on the other side. Slightly heavier, 40 kgs. That's 0.8 metres. Okay, first off, this mass, let's get that into weight, into newtons. Now, to be honest though, we're going to add this third mystery child who's going to be balanced in this situation here. Because all of their masses all of their weights are going to be their mass times g, you could kind of factor g out and just look in terms of masses, but let's not be lazy, let's do it properly. So let's look at turning forces. So for this child, the turning force is the mass of 30 kgs times 9.8 to get mass into weight, times the perpendicular distance from a pivot, which is 1.8 meters. So this child has a turning force of 30 times 9.8 times 1.8 meters. And they haven't given us any traps of the centimeters in this question. It's all meters, which is nice. So this child causes a turning force of 5 to 9.2 newton meters, and that's in the counterclockwise direction. Versus, on the other side, you've got this child of 40 times 9.8 times a distance of 0.8 meters, has a turning force of 313.6 newton meters. So this mystery child, whose mass is 45 kgs, they're going to balance the force. So let's get the child's weight first. 45 times 9.8. So the child has a weight of 441 newtons. Okay, now as it stands, this child is going to cause more of a turning force than this child. So the seesaw is going to go like that. So to balance it, we need more clockwise moment to balance out the total anti-clockwise. So we need the 529.2 Newton meters, and this in the counterclockwise direction has to be equal to the existing turning force caused by the child that's there, plus the turning force caused by the 441 newtons times whatever the distance that kid has to be. Sorry, I've gone off the page there a little bit. So we have the turning force from this kid is equal to the turning force caused by this child plus the missing one. So let's bring this for the cross and get the difference between them. 529.2 Newton meters minus 313.6 Newton meters is equal to 441 newtons times d. So let's get 529.2 minus 313.6 equals, and then that turning force of 215.6, we know that this child has a weight of 441 newtons. So let's bring it across to divide it in. It was multiplied by the distance. We're trying to isolate the distance, so bring this one across. 441 newtons. Divide your answer by 441, and hopefully we'll get a reasonably sensible answer. We do 0.48 recurring meters. So let's just round it off to 0.49 meters, and that's a sensible value. All right. If you found out that the child needed to be 2 kilometers away or something like that, you'd know things had gone wobbly. You do the old common sense check. So 0.49 meters, that seems like a sensible enough value for the child to be at. Okay, so last part. We got a merry-go-round. A simple merry-go-round consists of a flat disc that is rotated horizontally. A child of mass, blah, 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 blah. Okay, what do I want us to do? Draw a diagram showing the forces acting on the child as the merry-go-round rotates. Okay, let's just sketch it from the side. You can draw on the child if you need to, but we're really looking at forces. So the child has a weight, putting them down. Because of the rotation, at any one moment, he wants to move off at a tangent to the circle. So if I was looking at that from above, he wants to go flying off at that direction if there was no other force stopping that movement relative to the round of it. So in our diagram, his velocity is instantaneous linear velocity, wants to shoot him off in that direction, but there's a force stopping that from happening, dragging him toward, opposing that motion, and that force is friction, which is causing this circular path to result. Okay, draw a diagram done. What is the maximum angular velocity of the merry-go-round so that the child will not fall from it as it rotates? Okay, now unfortunately, if you're a little bit leery of circular motion, this is kind of where it starts coming back to haunt us a little bit. So the force that's causing this circular motion to happen is the friction. And the force of friction, if they give it to us, is 50 newtons. So that 50 newtons is equal to the force that is causing this child to, want to kind of want to shoot off into the distance. So we equate the two. The force of friction is equal to mass times the angular velocity squared times the radius. Now that's from the circular motion equations. Come back to haunt us. Now we know the mass. We know the distance because we're given it in the question. So we're looking for this fella here. So 50 newtons divided by the child's mass times the radius will be equal to the square of angular velocity. So let's get the square root of both sides. 50 newtons divided by the mass of the child is 32 times the radius that he's at is 2.2 meters. We'll worry about units right at the end is equal to the square root of all that. Will give us our answer in angular velocity. And we need to be careful, it's going to be in radians per second. But let's see, 50 divided by 32 divided by 2.2, and we need to get the square root of that. So we have 0.842, and we have to be careful here. If you remember back, these are in radians per second. That's how fast the child is rotating around. Okay, the last one, right? This is kind of a vague question. And depending on how deep you want to go in terms of frames of reference and general relativity, this could get very messy. So if there was no force of friction between the child and the merry-go-round, in what direction would the child move as the merry-go-round starts to rotate? Now, the thing is, if there is no friction, there'd be no movement. There's a whole number of ways you could argue. This is going to be kind of vague. But basically, one argument would be that the child would stay where they are. Because the reaction force keeping them upright is dependent on friction. So without that upright force, the gel could go like through the Earth. But more to the point, they're just going to stay where they are relative to the frame of reference. They're going to stay kind of stationary. It's a vague and badly thought out question to throw on a leaving cert paper. To be honest, that last little bit, those last little 5 marks. In fact, I'm going to do a rarity. I'm going to just check what I was looking for the mark scheme for that one. Do we have it here? Child remains stationary or any appropriate answer. For example, it depends on the frame of reference. Yeah, vague question. Right, that's the second of the higher level questions. I'm going to do a video on the ordinary level ones in a moment. Don't forget to keep cracking on the homeworks. The value of these videos is having tried them yourself. All right, there's no point just watching the video and watching me do a physics question. It's pointless and kind of boring. All right, when you've done them yourself, you get way more from it, and you can see where you went wrong, or just be quietly smug about how you got it right. Both are pleasant, you know. All right, guys, I'll talk to you soon.